Hey folks, welcome to another set of Chemistry 2 video notes. Today we're going to cover Chapter 13, which is all about chemical kinetics. In this chapter we learn the basics of chemical kinetics, the types of energy changes that occur in chemical reactions, what an activation energy is and how it affects reaction rates, how changes in concentration can affect the rate of a reaction, the orders of reaction, and how rate laws relate to reaction mechanisms. That's a lot to get through, so let's get started. We've talked before about the basic idea behind chemical reactions. Bonds are broken, atoms are rearranged, and new bonds are formed. You should remember from those discussions that it always takes energy to break bonds, and energy is always released when bonds are formed. Up until now, you've probably worked under the assumption that all of the bonds in the reactants molecules get broken, and the atoms then rearrange and form new bonds that make our products. That was an okay way to start thinking about chemical reactions when all we were concerned with was the reactants and products that we had. But it's far from reality. In this chapter, we're going to focus on what happens where that little arrow is between reactants and products. For example, in the combustion of methane, one methane molecule and two oxygen molecules react together to form one carbon dioxide molecule and two water molecules. In our previous way of thinking, we might expect that all three of those reactant molecules run into each other with enough energy and in the proper orientation at the same exact time. All of those bonds would be broken, and all of the free atoms would start forming new bonds in different arrangements, forming our product molecules. Even though that's technically one way that could possibly happen, it's highly unlikely to ever have any three molecules hit each other at exactly the same time, or for most molecules to collide with enough energy to break all of their bonds. What's more likely is that the reaction occurs in baby steps or elementary steps. Each of these steps only involves two molecules colliding, or just one molecule breaking itself apart, which are both much more likely and achievable scenarios than a simultaneous three-molecule collision. All of these elementary steps will add up to the overall reaction, the one we're used to seeing. That sequence of steps is what we call a reaction mechanism. Reaction mechanisms are extremely useful for understanding the energy changes and the speeds of our reactions, which we'll talk a lot more about throughout this chapter. We cannot directly observe each step in a reaction mechanism, but we can observe them indirectly by analyzing the rate or speed in which the overall reaction occurs based on various changes that we might make to the system. This comes up a lot in the last section of the chapter, so just keep that in the back of your mind for now. Studying chemical kinetics is really important for industrial chemists, as they can determine the best route in which to make a desired product, and they can increase their production yield by being very selective with the reaction mechanisms or finding ways to increase the reaction rates. One more thing you need to know before we move on is that a substitution reaction is one in which one atom or group of atoms replaces another atom or group of atoms in a molecule. The reaction shown here between the hydroxide ion and methyl bromide is a reaction we'll come back to a few times over this chapter. In this case, the hydroxide ion substitutes itself in place of the bromine in methyl bromide, making it a substitution reaction. In order to really understand a reaction's mechanism, it's helpful to understand the energy changes involved in a reaction. Most chemical reactions involve some net change in energy. That is, the combined energy of the products will be different than the combined energy of the reactants. If the products have more energy than the reactants, the reaction had to absorb or take in energy. We call these endothermic reactions because energy goes into the system. If the products have less energy than the reactants, energy must have been released during the reaction. We call these exothermic reactions because the energy exits the system. On occasion, the products will have the same amount of energy as the reactants. In this case, there's no net change in energy, so we call these energy neutral reactions. A great way to visualize these changes is by graphing them on a reaction energy profile. These graphs show the energy on the y-axis and the progression of the reaction on the x-axis. You can think of the x-axis like time, but without a unit. It's called the reaction coordinate and just shows us the start to finish of our reaction. To find the total change in energy of a system, we always take the energy of the products minus the energy of the reactants. Here's a couple of very simple reaction energy profiles. These are both just focused on the energy of the reactants and the products. If we start with reactants at a high energy, and then we go downhill to find the products at a lower energy, energy must have been released, so that's an exothermic reaction. Since the product's energy is smaller, taking a smaller number minus a bigger number gives you a negative. For exothermic reactions, the delta E, or the change in energy, will always be negative. The opposite is true for endothermic reactions. In this case, the reactants start out pretty low, and then you have to climb up a hill to get to the energy of your products. That means we had to put in energy to get up that hill. Mathematically, a larger number minus a smaller number will get you a positive delta E for the endothermic reactions. If the chemical equation for the reactions we've been looking at so far on our diagrams was just reactants yields products, then we've been talking about the forward direction for all of those reactions. What if we were to flip that equation and make it products yield reactants? This would be like looking at our reaction energy profiles from the right to the left, or from finish to start. Reverse reactions are extremely important and will come up a lot in this chapter and in the next. An important thing to note is that the magnitude of the energy change does not change, only the sign. If my products had 150 kilojoules of energy and my reactants had 80 kilojoules of energy, then in the forward direction, my reaction had a delta E of positive 70 kilojoules, because I take products minus reactant. That would be an endothermic reaction because my delta E is positive. In the reverse reaction, if I start with my products and it moves to the reactants are now the products, and the products are now the reactants. So I still take products minus reactants, it's just that this time they're on the flip side of the equation. So I would take 80 minus 150, and I would get negative 70, which is an exothermic reaction for the reverse reaction. At this point, you might be asking why reactions even involve energy changes at all. Where does that energy come from when it gets released to the surroundings in exothermic reaction? Where is energy stored when a reaction absorbs energy from its surroundings in endothermic reactions? The answer to those questions all have to do with chemical bonds. Each kind of bond between any certain two atoms is associated with a certain amount of energy. That's called its bond energy. The energy of a single bond between carbon and hydrogen is different than that of a single bond between hydrogen and hydrogen, or a double bond between carbon and carbon. When the number and types of bonds change, there's likely to be an overall change in those bond energies. This calculation is slightly different than the one we've seen before. Like before, if we know how much energy our reactants and products have, we can take the products minus the reactants to find the overall energy change. If we only know the bond energies, we can't quite do that. What we can do is assume again that all bonds are broken before new ones are formed. It's not realistically accurate, but it gets us to the correct answer. In this case, we add the total amount of bond energy in the reactants, because we have to add that energy to break all of those bonds. Then we would subtract the total bond energy of all of the products bonds, because when those bonds form, they release energy. You can also think of it as the positive total bond energy of the reactants plus the negative total bond energy of the products. If it takes more energy to break all of the bonds than gets released when forming new ones, we have an endothermic reaction. If more energy is released by forming new bonds than it takes to break our reactant bonds, then we have an exothermic reaction. No matter which way we're calculating the delta E for the reaction, if it's positive, it's endothermic, and if it's negative, it's exothermic. Now that we know the difference between the beginning and the end of our reaction, let's focus a little bit more on what happens during the reaction. The overall energy change of the reaction has no effect on the speed or rate of the chemical reaction. That rate is how we study our reaction mechanisms. To look at the rate, we have to focus on what happens between the beginning and the end of our reaction. Instead of drawing a straight line directly from the reactants to the products, there's almost always a little bit of a hill that the reactants have to get over before they can proceed to the products. The top of that hill is called the energy barrier, and it represents the energy of our transition state. The transition state is the intermediate, or in-between molecule that occurs as the reactants are transitioning to products. In the case of our hydroxide and methyl bromide reaction, that would be when the O in the OH just starts to bond with the carbon, while the bromine starts to break its bond away. You can think of this for any reaction where the reactants have gained just enough energy to stretch almost to the point where the bonds that are meant to be broken will be broken. and the new bonds that are meant to be formed in the products start to form. This intermediate or transition state is an extremely important molecule, and it plays a vital role in our reaction mechanism. The difference in energy between the reactants and that energy barrier, or the energy of the transition state, in other words, the height of that hill that the reactants have to climb before they move to the products, is known as the activation energy, abbreviated E with a little subscript A. Our reactant molecules must collide with at least that much energy in order to move on from the transition state to the products. The rate of our chemical reaction is directly dependent on that activation energy. The larger the activation energy is, the slower the reaction. Think of it like a hill or a set of stairs. It takes more energy to reach the top, so you end up going slower. The smaller the activation energy, the easier it is to overcome, so the faster the reaction occurs. The number of effective collisions is really the main determinant in how fast a reaction proceeds. An effective collision is one in which the molecules collide with enough energy to overcome the activation energy, and in which those molecules are oriented properly to react. For instance, when the OH ion collides with the methyl bromide molecules, the negatively charged oxygen must be oriented toward the methyl side of the methyl bromide. If it comes from the other side, or it's flipped around, a reaction does not occur. Increasing the temperature is always guaranteed to increase the reaction rate, because that means more molecules have enough energy to overcome the barrier. You can think of the temperature like the average amount of kinetic energy, or the average speed of the molecules. The higher the temperature is, the more energy the molecules have. So if we increase the temperature, more of our molecules will have enough energy when they collide that they can make it over that hill. We could also find a way to increase the number of collisions that occur with proper orientation. Just taking in those two factors, we can deduce that the reaction rate is equal to the number of collisions per unit time with enough energy to overcome the activation energy, multiplied by the fraction of collisions that have the proper molecule orientation. That orientation factor will always be a fraction between 0 and 1. 1 meaning that the orientation doesn't matter, and that all collisions that have enough energy will be effective. You can think of it like a fraction of how many of those molecules have the right orientation when they collide. We saw this diagram before, but let's look a little bit more closely. Notice how the hydrogen atoms don't break their bonds and reform new ones. They just shift into kind of a trigonal planar shape, with the OH loosely attached on one side and the bromine loosely attached on the other. This is a highly unstable molecule, which explains why the energy of the transition state is so high. This just helps to illustrate why our reaction energy profiles always end up with that little hill between the reactants and the products. You have to put energy into your reactants to get them to that high energy transition state. Once you do that, they'll continue reacting and go back downhill to the products. We talked about ways to make sure we overcome that energy barrier, mainly by increasing the number of effective collisions, by increasing the temperature. This is sometimes way too costly or even impossible to do because some reactants are sensitive to high temperatures. Instead of increasing the energy so that more collisions can climb that hill, what if we just make the hill smaller? We can do that through a catalyst. Catalysts can work in a number of ways to provide a more stable, lower energy transition state. This gives us a lower activation energy and a lower energy pathway to get from reactants to products. Catalysts often do participate in the reaction, but they'll get consumed in one step and then reproduced in another. So overall, they don't get used up, which is why it only takes a very small amount of catalyst to ensure a speedier reaction. That's also why we don't have to worry about including them in the overall balanced reaction. They do, however, participate in reactions, and they alter our reaction mechanism. Two ways in which catalysts can speed up a reaction are to weaken the existing bonds, making them easier to break, or by orienting molecules properly so that more of them are able to react. To illustrate the difference between a mechanism with or without a catalyst, let's look at the conversion of 2-propanol to 2-chloropropane. A simple way to substitute chlorine for the hydroxide in 2-propanol would be to break the OH bond and then replace it with the Cl, similar to what we did with the methyl bromide and hydroxide reaction. This can't be done like our methyl bromide reaction because the two CH3 groups on our carbon provide way too much clutter for the chlorine to come in from the backside. To break that hydroxide away from the carbon is a very, very slow elementary step, leaving us with a rather slow reaction overall. In the second mechanism, we add some zinc cation, and we also use hydrochloric acid as our source for chloride ions. The zinc can start to bond with the oxygen in OH. When it does that, it weakens the bond between oxygen and carbon. Since that oxygen and carbon bond is weaker, it's a lot quicker and easier to break. So that first step is still a slow step, but it occurs much more quickly than the slow step in the first mechanism. The next step is to go ahead and attach our chloride ion from hydrochloric acid to the positively charged carbon on our molecule. That positively charged carbon is known as the carbocation. Finally, we have to get the zinc ion back. So the hydroxide will leave the zinc to react with the positively charged hydrogens that came from our hydrochloric acid. And that makes water, and then we have our zinc 2+ ions back. That sounds like a lot more work to go through, but our first step, which was still a slow step, was not nearly as slow as it was in our first mechanism. And that gives us an overall speedier reaction. One type of catalyst that you encounter every day, whether you know it or not, are enzymes. These are catalysts that work inside your body to help speed up reactions. Each enzyme is specific to a certain molecule known as the substrate. There's a pocket in the enzyme known as the active site that just fits perfectly with the shape of the substrate molecule that the enzyme is targeting. They act similar to a lock and a key, the active site being the lock and the substrate the key. The active site in the enzyme will form intermolecular attractions to the substrate and help weaken some of its bonds, which allows the substrate to break down into smaller molecules that can then go on to participate in other important biological reactions. Enzymes can also grab onto the substrate and orient them in a particular way that increases the effect of collisions. One of the most important experimental methods we use to determine a suitable reaction mechanism is to change the concentration of one of our reactants and see how that affects the reaction rate. As we saw before, the reaction rate depends on the total number of collisions per unit time with the right amount of energy, and the fraction of those that have the proper orientation. We can break that energy factor down a little by saying that it's equal to the total number of collisions, all of the collisions, times the fraction of those that have enough energy to react. The fraction of collisions with enough energy, or the fraction of collisions with enough orientation, both depend on a lot of inherent factors. What's the temperature? Is there a catalyst present? What molecules are we working with? How hard is it to break bonds? If we're studying a reaction without changing its temperature or adding a catalyst, those two fractions remain constant. The total number of collisions, though, can be affected by how many reactant molecules you have in a given space. The higher the concentration of reactants, the greater the total number of collisions, and therefore the higher the reaction rate. Some common ways to increase concentration are by adding more reactants to a reaction vessel, decreasing the volume of a reaction vessel but keeping the same number of reactants, or, for reactions between a solid and a gas, turning the solid into a powder so that there's a greater number of molecules that can react with the gas at a time. Since our inherent factors don't change unless we change the temperature or add a catalyst, we're going to lump them together and call them K, the rate constant. This gives us our first glimpse into what a rate law looks like. The reaction rate is equal to the rate constant times the total number of collisions per unit time. If I had the general reaction A moles of A plus B moles of B yield P, we could say that the total number of collisions is related to the concentration of A times the concentration of B. Both of those concentrations with their own exponents, x and y. I want you to notice those brackets. They're not just there for decoration or to separate out parts of my equation. They stand for the concentration of. They cannot be replaced with parentheses. They're very intentional. So anytime you see brackets around something in chemistry, you can read that as the concentration of that something. Overall, we could say that the rate law is equal to K times the concentration of A to the xth power times the concentration of B to the yth power. The powers being the orders for the reaction. Notice that x and y are not labeled as lowercase a and b, the coefficients from our reaction. That's because they're not related to the coefficients in our overall equation. These exponents can only be found and confirmed through a kinetics experiment. A kinetics experiment is one in which we run the reaction once and then change one of our reactant concentrations to see how the rate is affected by that change. For instance, let's say I performed this reaction in a 1 liter vessel and I reacted 1 mole of A with 1 mole of B, and that produces 0.1 moles of P. I do that reaction again, but I double the concentration of A and keep the concentration of B the same. And I observe that instead of 0.1 moles of P, I make 0.2 moles of P. Effectively, I doubled the concentration of A, and that doubled my concentration of the product. When the reactant in question is doubled, and that produces double the product, we call that a first-order reaction with respect to that reactant. Being first order, that exponent x in my rate law is going to become 1. Now I do the experiment again, but this time I use 1 mole of A and 2 moles of B, keeping A the same as in trial 1, but doubling B. I notice that my P concentration goes from 0.1 to 0.4 molar. That's quadruple the product. When I double the concentration of one reactant, and that quadruples the product's concentration, that's known as a second-order reaction. Therefore, the y exponent in my rate law will become 2. If you think about what an exponent does, that should make sense. If I change the part inside the brackets, the concentration, from 1 to 2, that takes me from 1 squared to 2 squared. 1 squared is just 1, but 2 squared is 4. So for a second-order relationship, doubling the concentration of the reactant gives us quadruple the amount of product. If we were to change the concentration of a reactant and the rate doesn't change, that's called a zero-order reaction. Our exponent becomes 0, and then that term just becomes 1. It just disappears. It goes away. So if a reaction is zero order with respect to a certain reactant, that reactant doesn't show up in our rate law. There are other orders of reaction, such as fractional orders, but for the purposes of this class, we'll stick to 0, first, second, and the occasional third. So if we plug both of those orders into our rate law, we get that the rate law is equal to K times the concentration of A times the concentration of B squared. This is known as our experimental rate law because we found it through a kinetics experiment. As we said, we now know that this reaction is first order with respect to A and second order with respect to B. To find the overall order of the reaction, we simply add up all of our exponents. This reaction would be a third order reaction. As we mentioned before, most reactions do not occur as they're written in the overall reaction. They occur in a series of smaller reactions known as elementary steps. We also know that the exponents in our rate law cannot come from the coefficients of our overall reaction, simply because that overall reaction does not represent how the reaction takes place. We can, however, use coefficients from an elementary step to predict a rate law. To determine if a proposed mechanism is a plausible one, we still need to perform some kinetics experiments to determine the experimental rate law. Then, we look at the elementary steps and see if they will predict a rate law that's consistent with the experimental rate law. This is a must. For example, if I had the reaction A2 plus B2 gives me 2AB, and I determine that the experimental rate law is equal to K times the concentration of A squared, what possible mechanisms could I have? If I assumed that this happens in one step, just as the overall equation is written, I would predict a rate law of rate equals K times the concentration of A2 times the concentration of B2. To predict that rate law, all we do is write each reactant in the brackets and then use each one's coefficient as the exponent for it. This predicted rate law is not consistent with our experimental rate law, so it's not a possible mechanism. Mechanism 2 occurs in 3 steps as shown here. When you have more than one step, the first thing you need to do is make sure that all of those steps add together to give you the overall reaction. We'll do that on the next slide. Next, figure out which step is our slow step. Those will usually be labeled for you, but in this case, we're just going to assume that step 1 is our slow step. The slow step, or the step that reacts the slowest, is often called our rate-determining step. If all other steps move rather quickly, then the overall rate that we observe is pretty consistent with the slowest step that we have, because that slow step limits how fast the mechanism can proceed. Since the slow step limits the rate, we use it to predict our rate law. This time our rate would be K times the concentration of A2 times the concentration of A2, or simply K times the concentration of A2 squared. This is consistent with our experimental rate law, so it's definitely a possible reaction mechanism. When checking a mechanism to make sure it adds up to the overall reaction, you simply look for anything that exists on the reactants and the products. In this case, I've got A2 in my reactants on the first step, but then it's also in my products, so it can be canceled out. I've got 2 A's in the products of my first step, and then an A in the reactants in step 2, and again in step 3, so those can all cancel out. Whatever you don't end up crossing out, you just bring that down below and make sure it matches up with your overall reaction. In this case, it looks like it does. Just because we cross things out doesn't mean they don't exist or that they're unimportant. It just means that they don't show up in our overall reaction. Any species that gets produced in one step but shows up as a reactant later and gets consumed again is called a reaction intermediate. If the opposite is true for a species, it starts out in the reactants and gets consumed, but then later gets produced again, that's called a catalyst. For this reaction mechanism, we have A and AB2 that would be our reaction intermediates, and we don't really have any catalysts. If you're ever asked to come up with your own mechanism, or asked to select between a few mechanisms, here are some general rules. There should never be any elementary steps that involve a collision between more than two molecules. In other words, there should never be more than two molecules of reactants in an elementary step. Check to make sure the mechanism adds up to your overall reaction, and check to make sure the slow step, if there is more than one step, accurately predicts the experimental rate law. If all of those are true, it's important to remember that that just means that our mechanism is possible. Chemists would have to perform further experiments on the reaction to determine without a doubt which mechanism is the true mechanism. For instance, in our mechanism above, a chemist might perform a test to see if AB2 molecules ever exist in the reaction. If so, that's an indicator that our mechanism is probably true. Well, that's all for today, folks. As always, if you have any questions, let me know.